Hi everyone, my name is Yihao, and I'm the first year PhD student in Syracuse University. I'm now working with Kris on static analysis for binary.
Hello, my name is Jeffrey Ching. I'm now a master's student at Syracuse University. I'm working with Professor Kris Micinski, and I'm happy to be in this conference.
And I'm Assistant Professor Christopher Micinski of Syracuse University. I'm excited to be able to talk to you today about our recent work in declarative demand-driven reverse engineering. We'd like to offer a future for reverse engineering that harmonizes the best aspects of human intuition along with mechanized automated tools. So we're going to start with a little bit of motivation and background, and then we're going to discuss the high-level design and methodology behind the D3RE project. We're going to give a live demo using D3RE to perform an example reverse engineering task that we might do by hand right now using IDA-Pro or Ghidra. Then we're going to briefly remark upon our implementation and some of the mathematical formalism underlying D3RE. Next, we discuss our evaluation of D3RE. We evaluated our work in several different ways. Primarily, we re-implemented several currently existing Ghidra plugins using D3RE's declarative methodology. Happily, we found that this always led to terser code that was tighter and easier for us to understand. But we also found that because our system is using Soufflé, it was much faster than Ghidra most of the time. We'll wrap up by giving a reflection and some directions for future work, along with a brief conclusion.
According to some recent survey in reverse engineering area, we find that reverse engineer actually take iterative approach. And reverse engineer, they have a lot of tons of tools, and each tool is just for some specific phases. So as a reverse engineer, they need to swap between different tools. So a typical reverse engineering task will look like, first, you disassemble the code binary and load that into some tools like IDA-Pro or Binary Ninja or Hydra, so you can explore the code in the GUI interface, and maybe you wanted to see the control flow graph of this binary, and then maybe you want to do some further research on this binary. For example, you want to find crypto constant in this binary, like some constant in AES or other crypto algorithm. You want to find this static const. Then you may need to use some plugins in IDA-Pro, or if this kind of plugin does not exist, you need to write them by your hand. So the main reason why we want to use this tool is that we want to bring Datalog into reverse engineering area. Datalog is a declarative logic programming language, and it is very easy to write, and it's also very fast because there's some implementation, for example, Soufflé. According to its benchmark, it's much more faster than other constraint solver. It will be also very simple to write Datalog code to do reverse engineer, because there is a Datalog disassembler called DDSS. So we can directly use the intermediate relation inside DDSS. In there, they already has things like flattened facts of instructions and some facts about binary addresses, and it also already do some value analysis and define simple value analysis and define a user analysis. So current script engine inside some reverse engineering platform like IDA-Pro and Hydra is actually not that good. Because, for example, in Hydra, there's tons of scripts, but actually most of them is very simple scripts, like find cryptos and find some specific address in binary and pop up conditional jump, things like that. But for some complex tasks, if you wanted to do some traditional static analysis on there, pointer analysis or some much more complex one, there is some plugin, but not so much plugins can allow to do these things. But if you're using Datalog, it can make writing this code much more easier, because in Datalog you can see from here you don't need to iterate over things, iterate over instructions, and to do adding work stats or things like that. You just need to do some Datalog joins, then you can get what you want. So this is the workflow of our tool. So first, you load a binary inside Hydra, and then boot up our plugins, and you will get a repo. And when you have the repos, we will use DDSSM to build the metadatabase for your rules. So in your data log rules, you can directly use the rules inside DDSSM.
Yihao is now going to walk us through how we might use D3RE to do some common reverse engineering type tasks.
I use an example of how to write data log query to find the uninitialized variable inside small binary. The binary I use today is from Grammatex CGC repo. And this little binary is written in C and has a uninitialized variable inside, boundary inside. So first we can load this binary into Hydra. And then run our tools. And you can see here is our terminal interfaces. We have a lot of different commands inside. Before we load any kind of log query, we have already exported all the facts from a data log disassembler called DDSSM. We can see what we already have now. This is the rules we exported from DDSSM. So first of all, a very common case is that an uninitialized variable vulnerability happen is that we define a global variable, and then we forget it to initialize in somewhere else of the code. So in this case, we will focus on global variables. And because it's uninitialized usage, so it must be defined, used before the definition. So a very straightforward thought is that can we define a use-defined analysis in data log and to pop up all the defined usage chains. So we write a small data log script to do this. And we can load this script inside our tools. And then we can query the results. We can see there's a lot of defined usage chain about the global variables. We can click in Hydra to jump between this usage side or defined definition sides. Clearly, there's too much of these things. So we want to eliminate some of them. And then we can write a data log query to pop up all the global variables used before its definition. So the rule is here. So this means that we have a used global variable somewhere. But we use these negations to say that it's not defining something. And then we load this script inside our tools again. Then we should find that all the uninitialized global variables. You can see from here, there's still tons of this uninitialized, but not so much. In real cases, it can be much more than these things because we are just using a small, CGC challenges. So after this, we can check this call size by hand. But since there is a lot, we can still going to narrow down our search spaces. Datalog is quite good at doing that. We can edit our rules. And define a search spaces to search only the addresses. This addresses is actually the main like the address of main function, address range of main function. So we can always search the uninitialized variables inside main functions. Like this is just to narrow down searches, like to make like the result much more clear and much more easier to check by hand. Okay, and then we run these rules. We should get last concept. So this time we only get a few. And we can also highlight these different call sites inside Hydra using highlights. We can take a closer look of the possible uninitialized variable we find here. I also highlight the conditional jump during this area, because a very common case is that when people writing code, people usually they initialize the variable in some cases, but they forget to initialize it in some other cases. So if we're looking at this J and Z here, we can see the if jump here. Actually, if local 20 is not equal to these two values, the swap short and swap all won't be initialized, and the function called here will be an uninitialized variable. So let me explain a little bit about my data log rules here. So use before define global. This rule is used to pop up all the uninitialized variables. The first clause of this rule is if a global variable which is used but not defining anywhere, so we will consider it kind of uninitialized. Second clause is actually another very, very common case. If a variable is initialized, but it's initialized into non-pointer. If it's non-pointer, then we still consider it is an uninitialized variable. And this add highlight rule is used to tell Hydra highlight some edges here. And add comment is to tell Hydra, like, I want to add comment for some defined relations.
I'm now going to spend a few moments discussing the implementation behind our current D3RE prototype, along with some of the mathematical foundations that underlie how D3RE is implemented. D3RE is currently implemented as a prototype written in Python. Our main part of D3RE is what's called a metadatabase. This is a daemon that calls out to Souffle to do the relevant work, and then makes the relevant calls to Ghidra to visualize the results, along with accepting user input from the CLI that Yihao has been showing throughout this presentation. Whenever a user loads a binary into Ghidra, it gets processed by the metadatabase daemon. This metadatabase tracks and associates each datalog program and run along with the corresponding binary, and it associates that with a corresponding output database. You can think of the EDB as maintaining the fully materialized set of facts as dictated by the combination of the rules and the input database. To analyze a binary, a user types commands into a REPL, which then subsequently sends commands to the metadatabase daemon. This communication happens using protobufs under the hood to anticipate scalability going forward. We want to be able to ship large amounts of facts and databases between the metadatabase and the REPL that's going to be able to then visualize those facts using Ghidra. We're currently using a plugin using Ghidra Bridge to communicate with Ghidra. However, this is a pretty poor solution because it requires a lot of security compromises. And going forward, one of the first things we plan to do is to replace Ghidra Bridge with our own custom Ghidra extension. Now I'm going to briefly discuss the theory behind D3RE. Now, D3RE exploits one basic fact about datalog. Datalog is monotonic. That means you're strictly going to add more and more and more facts as you learn more about the program. In practice, there are occasionally times in which you might want to handle non-monotonicity. So for example, you might want to remove facts from the database. We can handle that as well. D3RE exploits this monotonicity to cache databases And if you have a subsequent query that you want to make about a program, D3RE will figure out which database to use, and it'll figure that out based on trying to figure out what is the most or best database we could start with that has the most facts to start from. So imagine that you're going to do a very high overhead query, like trying to run DataSystem for the first time. Well, that call may take several hundred seconds, for example, to process the binary. You may want it to happen in the background. However, using that EDB, we can then bootstrap invocations for subsequent rules, which will allow those subsequent invocations to be very fast, assuming they don't rely on too much computation delta from the original EDB that we start with. Now we're going to discuss our evaluation of D3RE. We evaluated D3RE in several ways. The main one was to re-implement several currently existing Ghidra plugins using D3RE's data log. Yihao will now discuss a re-implementation of a cryptographic plugin from Ghidra re-implemented using D3RE, and then we'll discuss various performance benchmarks we ran.
So let's give a further comparison of Ghidra plugin written in Python and the plugin written in data log. So this is a little Python plugin to find crypto constant inside a binary. The crypto constants like AES and CRC's crypto constants. There's two kinds of constants to find. The first is like constant inside the operand, instructions operand. So if in Python, like you need to iterate over all the instructions and try to compare each operators there. But for the second kind of cryptos, which is a very long binary sequences. In Python, it just like do a search of whole binary file to find this long binary sequences. It's only one line and very fast. And then this is a data log version of doing the same things. For the first kind of constant, which is constant in the operand of the instruction, it is very easy to do so. You can see you just need to do a data log join of the constant value and the operator value. That's very fast and easy. But actually for the second kind of like long binary sequences, it's not so easy because in data log you can only compare data like word by word or byte by byte. You can do a like recursively reasoning and recursively compare of things, but it's very slow. Like a quicker way should be like just compare the head of the head the first 10 bytes or first 10 words of the whole binary sequences. It's quick. In this way, it's quick, but it's not so precise. So one directly benefit you can get from using data log is that you can write short code. Basically, the reason is that the AST is a structural data. So if you wanted to like go through AST, in Python, let's say, like you need to iterate over things and then go into different like substructure. But since in data log every fact is flattened, so you get a flattened AST, you just need to do a data log join on there. And the other things that if you want to like implement, for example, some working list style or static analysis, like in like normal imperative language, you may need to like write a long code but to compute the fixed point. But in data log, due to its semantic, like you can compute fixed point very easily, and you can guarantee your program terminates. We also compare the running time of originally Hydra Python plugins engine and our data log plugin engine. So you can see that in many cases our tool is faster because like the data log engine like Souffle, it has a very efficient index selection algorithm, and it also has a very efficient data structure to store the facts. But in Python, since it's very open and you can you can write some silly code and like use some stupid data structures to store things, But it's not every case that Datalog will be faster, and we will talk this later in later section.
Now I'd like to briefly discuss our plans for the future of D3RE. Now currently D3RE is just a prototype. There are a ton of limitations to using it in practice that we have to work out. Now another potential limitation of D3RE is that we're doing computation outside of Ghidra, and that means we have to go across a process boundary. There are occasionally going to be times when it might be very cheap to just update facts very quickly, and there are other groups who are looking into integrating Datalog into Ghidra itself. But also, looking into the future, we'd like to accommodate other kinds of backends as well. So in some related work, my collaborators and I, Thomas Gilray and Siddharth Kumar, have been working on a compiler for Datalog down to parallel relational algebra. This is a version of Datalog that essentially runs on supercomputers. You can run it on arbitrarily many nodes at a time. We've been running it on 1 to 2,000 process counts to do basic computations such as KCFA for program analysis. And we plan to build out the rest of our infrastructure on D3RE on these kinds of backends and then ship their results so that we can do extremely high performance analyses over binaries using large supercomputers. I should say we also hope to extend Datalog to allow you to make queries to things like SAT solvers. My student Arash is working on that right now. We also want to continue to follow up on some of our previous work in thinking about what user studies would look like for reverse engineering tools. In fact, we'd like to pin down precisely what kinds of GUIs could we use to help reverse engineers interactively craft these queries. There's some really cool related work here. A few years ago, there were some authors who created this work named Ponce, which is a GUI-based symbolic execution plugin for IDA Pro. We'd like to offer similar kinds of facilities using an extension of Datalog, plus this high-performance backend I just discussed.
Thank you so much for listening to our presentations. Now we'll accept any questions.